This lecture video is a video showing you how to solve circuits with Kirchhoff's loop rule and current junction rules. It's important to note that in these problems where you're going to use Kirchhoff's loop rule, in general, you also have to use the current junction rule, because Kirchhoff's loop rules aren't going to give you enough equations to solve your algebra problem, it turns out. So in order to learn how to use Kirchhoff's loop rule, it's based on having a good idea of what a voltage drop is. And so in the example I'm going to show you in this lecture, there's only going to be two different kinds of voltage drops. There's going to be a voltage drop associated with going across a battery. So it's voltage drops associated with batteries, right? Batteries hold potential differences. And also there's voltage drops associated with resistors, in particular resistors with current. If a resistor doesn't have any current at all, then that means there's not going to be a voltage drop. There's only voltage drops across resistors with current. Okay, so let's do the voltage drop across a battery. So if your path, so Kirchhoff's loop rule considers a path around a circuit, and if your path, which is denoted by this red arrow, goes from the short plate side over across the battery to the long plate side, can you see that that's from left to right for this red arrow? If your Kirchhoff loop rule goes from the low to the high, that's actually not a drop, it's a gain. And you'll see me when I deal with voltage gains, I'm going to put them in as negative drops. So a gain is a negative drop. But if your Kirchhoff loop rule actually was traversing the battery, going across from the high potential side over to the low potential side, it's genuinely a drop. And we're going to put that voltage drop in with a plus sign. When you go across a resistor, in order to know whether or not you are looking at a voltage gain or a voltage drop, you have to look at the current direction. In particular, because you have, this voltage gain and voltage drop and use of Kirchhoff's loop rule, it's usually associated with trying to solve for a current, because a current in these circuits would be one of your unknowns. So you want to solve for it. Not only do you want to know how much current it is, but you actually need to also know the direction of the current. So those are two pieces of information. It's almost as if you're trying to solve for a vector. So in these problems, you're going to see me have to make an assumption. That is, I'm going to claim, right? Maybe I have a good idea that the current must be in a particular direction, or I actually, from the information given, can't quite tell which way the current is going to flow. So what I have to do is I have to guess, or I have to assume a current direction. So the blue arrow towards the right is my assumed direction of current, and I is the amount of current. So when I go across a resistor, if I take a Kirchhoff's loop rule path that goes from the left side to the right side, that is with the current, that's called a drop. But if I go from the right side to the left side, that is, I go against the flow of my assumed current, that's actually a gain, right? Current actually flows downhill. It flows from the high side down to the low side, just like water would. So it's considered a drop if you move across the resistor in the direction of the flow of the current, your assumed direction. And it's a gain if you go up the hill instead, if you go against the flow of the current up the resistor, right? It's called a gain. And in that case, I would put the voltage, but with a minus sign. So Kirchhoff's loop rule, the statement of it is that if you add up all the drops and the negative gains, right, on any closed loop in a circuit, it is always zero. That's what Kirchhoff's loop rule is. Kirchhoff's loop rule says that the sum of the drops on any closed loop in a circuit is zero. And I'm going to use Kirchhoff's loop rule to analyze this particular circuit. So you can see that I've got a battery over here. I've got a resistor actually directly connected in series with this battery. But then there's a junction. And at the junction, you can see that if I go down, I'll be going backwards against this battery, right? Actually, if you think about it, this battery, V2, and this battery, V1, both tend to want to push current upwards, right? And then there's this other resistor over here. Notice actually that your series and parallel rules for equivalent resistances, they aren't going to help you in this problem. Because these two resistors, the problem is I've mixed in a battery. In fact, actually, the resistor R1 is in series with the parallel combination of a battery and a resistor. So I can't use those equivalent resistor rules to solve my circuit, right? So for circuits like this, where you can't find only parallel and series combinations of resistors, which is this particular circuit, you have to resort to something else in order to solve the problem. And Kirchhoff's loop rule is the something else. Okay, so this is the circuit we're going to solve. I gave both voltages and I gave both resistances. And this is the network of how those circuit devices are connected, right? So the network information is in the diagram, but the values of the individual circuit elements is in this list of 4 values, right? 10 volts, 2 volts, 20 ohms, 10 ohms. Okay, so I'm going to use Kirchhoff's loop rule. I'm about to use these voltage drop rules. And I need to, in order to start doing that though, right, I need to assume some currents. So let me go in and assume some currents. I'm going to change the color to red. So I'm going to assume that the current goes this way, right? So it goes towards the right through resistor 1. I'm going to call it I1. So that current, right, must have been coming around from here too. So this is also I1. Another assumption I'm going to make is that the current here, I'm going to call it I3 because I'm going to reserve the current label I2 to be the current that flows through resistor 2. And it continues around the corner here, right? So actually, let me clear it up just a bit. Oops. Let's say that my assumed current direction for I3, is up through the battery V2. Okay, so these are assumed currents, right? And both, we're talking assumptions about both. Well, actually, it's not really, we're labeling the magnitudes, right? And assumed the directions. All right, so the sum of the drops on any closed loop in a circuit is 0. So let me label a closed loop. I'm going to start here, and I'm going to go around this way and stop there. Can you see that this is closed. It's closed because it starts and finishes at the same conducting place, right? It starts on this wire down here and goes around in a loop and finishes at the same conductor. It's important that it is closed, right? This is a closed loop. I'm going to have another closed loop. I'll label it in this red, and it's not really important that I do this, but I need to choose. So I'm just going to choose that it goes around also in this clockwise sense, but it's this other loop over here. Okay. So let me just start with these two, and then I might have to consider a third one, which I'll go ahead and label now, that maybe starts on this lower conductor and just goes around on the outside instead and finishes on the lower conductor. All right, so I've got these three loops, but let's treat the blue one first. So here's the blue loop. So the sum of the drops on any closed loop in a circuit is 0. So 0 equals the sum of the drops. So let's go and look, right? So here is, you can see where I'm looking, right? I'm looking right here at my starting point in the loop. And as I go around the loop, the first thing I encounter along my loop is going across a battery voltage. But I'm going from the short plate side to the long plate side, so that is a gain, right? So as I go across and gain, I have to put that in as not a positive drop, but a negative drop. The voltage is 10 volts, so it is negative 10 volts. So the next thing I go through is I go across the resistor R1, right? So I'm moving along this blue circuit loop, right? And I'm going across the resistor from left to right, but my assumed current, I1, is assumed to also travel through the resistor from left to right. So that actually is a drop. So I'm going to put it in with a plus. So the drop is assumed current I1 headed towards the right times R1. But I'm not finished, right? If I continue traversing on my Kirchoff loop, I'm going to go across the battery V2, but actually this time I'm going to drop, right? Because I'm going backwards. I'm going from the high side down to the low side. So that actually is another drop. And the drop this time is 2 volts. And I am, right, adding the drops together because literally it says sum of the drops. So I want to add negative 10 volts to I1 R1 and to positive 2 volts, and I get 0. And you can see that there's only one unknown in this formula, or this equation, because R1 is up here, 20 ohms. Before I solve it though, let's go and write down the Kirchoff loop rule we get from doing the red cycle. So 0 equals the sum of the drops. So right, once again, if I start on this low conductor, the first thing I get to is the battery, but I'm doing a gain. So that goes in with a minus sign. So negative 2 volts. And then when I go, so the very next thing on this cycle is R2, and I am going through with my assumed current direction I2, right? Which means it is a drop, right? And here I have two equations. And each of these equations, lucky for me, although problems can be more complicated than this, but each of these Kirchoff loops actually gives me I1 all by itself and I2 all by itself. So this problem actually, this circuit is not complicated enough to mix up various unknowns all in the same equation. But in more complicated Kirchoff loop rule problems, in general, you'll have a mixture of currents in each Kirchoff loop, right? So yeah, so you'll have a more interesting, difficult problem to do. But anyways, I've done enough actually to get I1 and I2 all by itself. For fun, actually, let's go and do the green loop real quick. So the green loop, unfortunately, I think you can see it's going to go clockwise. So the green loop, right, is also the drops are going to add up to 0. So I start on down here, and the first thing I get to is this battery, which is a gain, negative 10 volts. And then I go through the resistor R1, but with my current direction. So that's my assumed current direction. So I go with it. That's a drop, so I put it in positive, right? I1, R1. And then the next thing I go through, notice that I'm not going to go down this leg because the green cycle just keeps on going, right? Keeps on going, and now it goes through R2 in the direction of the assumed current, I2. So it's a drop, goes with a positive sign. And then I just keep on going, and notice that I have finished when I get here. I don't need to go up this middle leg, so I'm done, right? And that is this. But if you look really carefully, right, this is a Kirchoff loop that actually has both unknowns in it. But I'd like you to notice something. This third loop is a linear combo of the red loop and the blue loop. It's a linear combination of the red and the blue, right? All you have to do to see that is solve for the 2 volts, right? Move the 2 volts over to the left-hand side, and you get 2 volts equals I2 R2. And if you then take that 2 volts, right, and put it here, then what you're replacing the 2 volts with is I2 R2. So just these two equations right here, they're actually identical to this third equation. So they're not, there's a linear independence issue. So this third equation is not new information. It does not add to it. And you'll see in general that in a sense, the blue curve and the red curve add together to give you the green curve. And it's because the blue curve travels across this battery backwards, but the red curve travels across it forwards. So when you add the two curves together, or the two cycles together, that traverse of the battery, which happened backwards and then forwards, they cancel. Because for the blue cycle, it's a drop, but for the red cycle, it's a gain. So if you add the two cycles together, you get the green cycle, and the middle leg is canceled algebraically. Okay, so we didn't actually need to do the third one. And if we thought about it a little bit, you would have seen that you don't get any new information. Yeah. Okay, so let's solve the blue problem and the red problem. So if you solve the blue problem, what you're going to do is you're going to get a value for I1. So I'm going to do the algebra a little bit quick, but I'll tell you what I do. So put 10 volts over to the left, subtract 2 volts, so left over is 8 volts, right? And what's left over on the right-hand side is I1 times R1. So the unknown current is 8 volts divided by the resistance 20 ohms. And then this thing right here, I'm going to try to be clever, so copy, paste. So the red cycle here, right, move the 2 volts over, divide by R2, so you get 2 volts, and then R2 is 10 ohms. And that's what I2 is. Okay, so, right, these are numbers, right? They're currents. I'm going to do a little simplifying. So I1 is, if I divide by 4, I'll get 2 over 5. And over here, if I divide by 2 on top and bottom, I get 1 over 5. Right? So that means that 2 over 5 amps, 1 over 5 amps. Okay, so, but what about I3? my Kirchoff loops. Actually, I've done every possible loop, right? And unfortunately, I3 was never in any of the loops. So how do I get I3? Well, let's think a little bit about what I have so far. I1 is 2/5 of an amp. So 2/5 of an amp is running to this through this resistor and running into this junction. And then, but what's also showing up at the junction is I3 going upwards and I2 leaving. So let's use the junction rule, because the junction rule is going to tell us about the relationship of the currents going into a junction, which is I1 and I3, and the current leaving the junction, which is just I2. So the loop rule says that I2 leaves the junction, I1 and I3 come into the junction. So this is the junction rule. And what you can see is it must be used, right? The junction rule is in general going to be your last equations that are going to make it so you can have a complete algebra solution, right? We had all kinds of equations. In fact, we had, two equations with two unknowns, I1 and I2, and we could solve for I1 and I2, but it wasn't enough to give us I3, so we needed a third equation. The third equation comes from the junction rule. The junction rule in general, you have to use it, right? There's actually two junctions. There's this upper junction and this lower junction in this problem. But if you write down the junction rule for the lower junction, it will just say this again. It's the same junction rule, actually. Okay, so now I3 equals I2 minus I1 equals, so I2 is 1/5 of an amp, and I1, right, I have to subtract it, 2/5 of an amp. And the answer is that I3 is negative 1/5 of an amp. Why negative? Oops. My assumption, my assumed current direction for I3 must have been incorrect. But Kirchhoff's loop rule and junction rule save the day. They tell me that if I was to go up in my problem and simply assume that the current goes backwards through this V2 battery, then everything would have come out as plus signs, but all you would have gotten is that the current I3, if you assumed it to have the other direction, it would have come out as positive 1/5 of an amp. But the truth is it's not a bad assumption that a battery is going to be capable of pushing, ultimately, a current forwards through itself, right? This orientation of battery tends to want to push current upwards, just like this one does, right? But it turns out that this battery over here on the left was so strong compared to this weaker battery that actually this battery is ultimately able to push current backwards through the battery V2. And this is actually a recharging situation where if the V2 battery was a rechargeable battery, it has current running through it backwards that is going to re-energize the battery V2. So V2 has a current running backwards, and this is a recharging scenario, right? So I'd like to point out something. So if I do the power, let's power by battery 1, right? So let's think about power. It's the voltage times the current, right? So it's V times V1 times I1. So V1 is 10 volts, and I1 is 2/5 of an amp. So it's I1 times V1, and it's equal to, so I1 was 2/5 of an amp, and V1 was 10 volts, and so multiplying, right, 10 over 5 is 2, so you get 4, and it's watts, or 4 joules per second, right? But this actually is rate of energy loss by battery. If I look at the power of V2, right, V2 actually has a current running backwards. So, right, it has a current running through it backwards, and so be careful, because actually if you look, the current running through V2 is 1/5 of an amp actually running backwards, and it's actually got the label I3, right? So it will be I3 V2, right, multiplied. So I3 is actually a negative current. It runs backwards through the battery. So I'm going to put negative 1/5 of an amp, but the voltage is 2 volts, right? And so I've got this negative sign, which you interpret to be a case where this is the rate of energy accumulation, right? Because this is recharge. All right. Thanks for listening.